All right, so I'm going to try and make this interesting as I can. We're going to introduce OpenGL on iOS with C# using Xamarin tools. So I'm going to assume no knowledge of OpenGL whatsoever, and so we'll go from there. And I apologize for my non-slides. These are mainly cues to remind me what I'm talking about. OpenGL is going to seem very foreign, especially when you sit down in like C# world. OpenGL goes back to 1992 when it was opened up and was actually used prior to that. It was invented by SGI and then it standardized and opened up in 92. So it was mainly a C API and really a good model, a good way to think about it is like this is just a C API for sending commands to a SIMD, that single instruction, multiple data, vector supercomputer with some graphics bias. And the funny thing is like over the years, the graphics bias has actually gone down. So if you see the API these days, it's less obviously used for graphics. It's more general purpose than it was before. That makes it harder to use. That makes it harder to do graphics, but it's extraordinarily flexible. So a funny side effect is OpenGL is a necessary but not sufficient element to do graphics, to do GPU accelerated graphics on iOS or most hardware. And we'll talk about some of the things that OpenGL is missing. But basically OpenGL does not provide everything you need. It's just about sending the graphics commands to the GPU. OpenTK is the way that we will be using OpenGL today. OpenTK is a cross-platform .NET wrapper for OpenGL. OpenGL is really only a native C API. OpenTK provides almost a one-to-one wrapper on top of that with a little bit more to basically fill in the gaps where OpenGL is missing some things. Prerequisites to be able to use this. One is you need to know some of the nuances of monotouch. The main nuance that I encountered with monotouch is that you cannot just use any .NET library. You have to reference the .NET. You have to reference the monotouch flavor of that library. And I'm not going to mention portable class libraries. Andrew was talking about that earlier. There is a possibility that you could use a portable class library, but historically, for the most part, you have to use a monotouch build of an assembly. Vector arithmetic, which we've covered offline, you need to have some idea of what you're doing there, and that matrix multiplication can be used for representing all manner of transformations. And then the other prerequisite, if you're going to be using OpenGL ES2, which probably you are, then you need to understand GPU programming with shaders, and I'm going to talk about that. So some tips. Start simple, especially if you're new to OpenGL. Your first program should be extremely simple. Start with something that works. Start with a working demo and modify it. There are many gotchas, and I'm going to cover a lot of those. But there's just many ways, and OpenGL does not help you. So one of the tips that I like to give is to know what your default projection is. So if you just want to draw some points or lines or triangles on the screen and not doing any fancy projections, you just want to make sure, hey, I have a render context I can draw. Your default projection is -1 to 1 in all three directions. -1 to 1, 0 in the center. And that's the case on most hardware that I know of. So that means if you give a z coordinate that is 2, your point, even though it might be right in front of you, your point may not be drawn. So -1 to 1 in all three directions, otherwise it'll be clipped. And this is going to seem like a very strange tip in a talk about OpenGL, but the tip is don't use OpenGL. Use a higher level API if it makes sense. I'm an OpenGL guy, but even I will try and get myself up above OpenGL as quickly as I can, up to higher levels of abstraction. So again, I know that probably seems very strange for me to say that at a talk about OpenGL, but it's true. Like if you don't, I mean, if you're really hardcore and you just like to do interesting and hard things, don't, go for it, and I'll be here to help you. But if you're talking about business case and your own time versus value, you should evaluate other higher level libraries. The one that I will single out is Monogame. That one generally is very good cross-platform. The API is very nice. It's based on XNA, which was originally developed by Microsoft. As far as I know, Microsoft doesn't support XNA anymore, but the open source community has kind of picked up where it left off. And funny anecdote, there are games in the Windows Store that were built on Monogame because XNA does not work in the Windows Store, last I checked. So that's kind of a funny thing. Some examples of the things that OpenGL is missing. It doesn't help you create a window or device context. So if you wanted to start at square one, you could not. If you were doing this in the old Windows days, you had to use MFC or Win32 APIs to get your HWin, your window handle, and only then after you could create a context, a device context, could you start using OpenGL commands. OpenGL requires there be some kind of context, but it doesn't help you create it. It relies on the operating system to do that. Xamarin does help us there. There's no input. There's virtually no concept of input in OpenGL. So like if you want to write an app where you click on a particular point, and interact, like I would imagine that you're making a game where you tap on something or slash something and want to know what you hit. OpenGL, for the most part, won't help you with that. There's no file I/O, and we need to, typically read shaders from files. OpenGL won't help you with that. There's really no concept of a camera, which is strange. There's even no help, like we talked all about how important vector math is, and basically they don't help you on the CPU side. They don't help you with the vector math. Again, OpenTEK will come and fill in the gaps there, or Monogame if you're using that. Again, this is a C-level API. There's virtually no complex types. There's no concept of an object. They use the terms like objects and buffers and texture maps and vertices, but at the end of the day, a lot of time, all you are using to refer to those things is an integer. Okay, so I might have an integer that refers to a particular shader on the graphics card, or an integer that refers to a particular buffer, but you don't have this like complex type system. So again, it's great to understand these things. All of these APIs have to use OpenGL under the hood on everything but Windows Store. OpenGL is a great API, a long-lived API. It's not going away anytime soon. So it's important, but again, not everybody has to go all the way down to the middle. All right, what are its benefits? I talked about why it's bad. It's highly portable. Microsoft, this is my personal opinion, Microsoft has been trying to kind of kill it for a long time. They removed themselves from the OpenGL consortium probably around 8 or 10 years ago. And when Windows Vista first came out and they had like the better presentation experience, their party line, what they said was that we will not support the Windows Vista Aero experience and OpenGL. You get one or the other. But so many developers objected, especially those in the scientific and CAD world, that they finally conceded. But in my opinion, the reason that Microsoft did that is just to find out how many people were actually using it, what the uproar would be like. In Windows Store, they officially stopped supporting OpenGL. So if you're writing a Windows Store app, you need something to help. Good news is there are projects. I think Steam just released a public or open source API that looks like OpenGL, but it's Direct3D on the inside. And then there's Google has the opposite. Google has a project called Angle, which is Direct3D on the outside, but OpenGL on the inside. So you're not stuck if you have a bunch of OpenGL code. It's highly portable, very, very, very fast. So reasons that you might be interested in using OpenGL, you're trying to draw some interactive graphic. It comes up a lot where you're doing something, you're learning, you're plotting some points, and all of a sudden your user needs to plot like, instead of 100 points, they need to plot like 10,000 points, and all of a sudden your JavaScript library or your simple graphing library is just grinds to a halt. OpenGL is for this. Games, obviously. Abstractly, the things that it's really good at is SIMD. So in computer science, what we call vector computing. So like 2D, 3D, 4D vector computing. And they have things that are often done in graphics, like interpolation, or mathematics, we call those like linear combinations or bilinear interpolation. It's extremely fast at that. It has customized hardware on the GPU to do those things. Quick history. Sean alluded to using the GL or iOS GL at Silicon Graphics pre-92. These days, it's managed by a group called the Kronos Group, which is a consortium supported by probably the biggest players would be like Apple and other Google, other big companies that rely on this. Another benefit to learning OpenGL, OpenGL ES, the embedded version that we will talk about, is that it's very similar to WebGL. WebGL is an up-and-coming technology for doing 3D graphics in the web browser, and it's going to become very important. Okay, some history that's relevant to you that you may encounter. So we need to talk about the concept of the pipeline. So in graphics, typically we talk about things moving through a pipeline. So at the beginning of the pipeline, I have like points, I have vertices. So a vertex, that's just the corner of your object, geometric vertex. And then I have the space that's filled in between those vertices. I have polygons, and I want to transform those polygons. I want to light them, I want to shade them, and then I'll project them onto the flat screen. You can think about those stages that I talked about as like discrete stages in a pipeline, and it's really helpful to think about this concept. So historically, we have a stage called like transform, and another stage called like lighting or shading. And so in general today we're going to talk about what's called like the vertex stage or the vertex shader, and the fragment stage or the fragment shader. And generally the vertex stage is used for transforming points, basically from 3D to 2D, and the fragment stage is used for coloring pixels, actually filling in the gaps between the points, what we call fragments. The reason they're called fragments is like normally you deal with triangles, but triangles can get cut off and occluded. So at the end of the day, it may not really be shaped like a triangle. So we call them fragments. That's also known as the pixel shader. Or, all right. Fixed function was what we used before the pipeline. The stages in the pipeline are programmable. So I was talking about these stages. You have these discrete stages. These days, you can make each stage do what you want it to do. It's highly programmable. It's basically, you can do anything you want. But it's still, you have these broken up stages. The output of one stage feeds into the input of the next stage. Back in the fixed function days, you still had these stages, but they were programmed for you. So the vertex stage would basically, it would transform things using a matrix, like a perspective projection matrix, and that's it. You couldn't do anything else with those points. And the pixel stage would basically do something like Garot shading, where basically you color each vertex and then maybe you interpolate those colors between the vertices. Today, you can do anything you want. It's fully programmable. Each one of those stages, you can write a custom program for each stage. So that's the difference between the fixed function pipeline and the programmable pipeline. OpenGL ES2 is entirely programmable. You cannot use the fixed function pipeline in OpenGL ES2. If you're targeting the modern iPhones or modern iPads, basically anything since the first iPod, you'll be using ES2. So I'm not going to spend any time talking about ES1, the fixed function. Another thing that you might hear or read about, but again, I'm not going to talk about this, is direct mode versus retain mode. Direct mode, what that means is like you issue a command, draw a triangle, it happens right that moment. These days we deal in retain mode. Retain modes means you bundle up, you batch up a bunch of like triangles and vertices, and you ship those all over to the graphics card, and then you tell the graphics card, hey, when it comes time to draw those polygons that I gave you, that you have in your memory. Again, nuances that we talked about. Generally, OpenGL is kind of one way. You send commands to OpenGL, and generally speaking, you don't get anything back. You can, but it's usually slow and not practical. So the other weird thing is it's very highly state-based. So if you're a really great programmer and you've liberated yourself from global variables and side effects, well, OpenGL only works based on those things. So we'll see that when we see the code. It's very side effect driven. And like I mentioned earlier, there are no objects, there are no complex types. Typically when you're talking about a particular thing, the only way you have to refer to that thing is by an integer. Or it may just be implicitly in the state. So I think I've already defined what ES 2.0 is. EAGL is a part of the standard that helps you get a device context on mobile platforms. And so when you see that prefix, generally you probably won't have to worry about it. But that's what that refers to. And I want to just highlight one thing, another kind of like a mental model of what's going on, is that at the end of the day, a lot of what we're doing is we're just mapping things that are on the CPU in main memory to the GPU in GPU memory. Some devices have shared memory. We don't worry about that. Well, we can, but basically there's a lot of different ways to basically map things from this one world that we are used to living in to this other world. Again, the idea that I think is very helpful is that inside your phone is another separate supercomputer. You have the normal processor that you're using all the time, but there's this other supercomputer just sitting there, the GPU. And really it is like, it's more powerful than a Cray supercomputer. It's a supercomputer just sitting inside your phone. So so the mental concept is like, it's remote and it's removed from me, and I kind of have to like send the data over there and send programs over there. Is helpful for understanding the way that OpenGL works. All right, so finally, we're going to look at some code, 8:30. OpenTK, you're going to pull in, you select which version, which flavor of OpenGL you're going to be using by which namespace you pull in. So you're going to probably be just using opentk.graphics.es20. That means Embedded System 2.0. Okay. So I want to just show you a couple examples of shader programs. Another historical note, the reason these are called shader programs is the first concept of a shader really was used for shading. So originally, back in the 70s, shading was just talking about like, oh, what are the different ways that we can very loosely approximate the way that light bounces off of the surface and gives it some color and shading. And pretty quickly people realized, you know what, we have very complicated surfaces. Just in this room, we have like the aluminum highly reflective surface over there. We have the sort of matte surface back there. The ways that you would approximate or model these shading are very different. So basically, you can't use a one-size-fits-all approach to shading. And so people started realizing, you know what, we need complicated ways, more modular, customizable ways to model shading. The first, for those of you interested in the historic background, you can look for a paper called Shade Trees by Cook. And the original concept was like, we're going to build up these trees. And it's like, oh, I go down this branch if I'm like this. I go down this branch if I'm like this. Well, that's just a programming language. I mean, you're just talking about if this, otherwise this. Okay, so that's why they're called shaders. These days, shader is kind of a misnomer because we use these shaders or GPU programs to program stages in the pipeline, and probably only one of them has anything to do with shading. And if you look at modern pipelines, we're only going to talk about two. The modern pipeline could have, like, I think more than 4 stages. But most of the time you can get away with just worrying about 2. The vertex stage is just responsible for transforming vertices. And I'm going to show you the most simple vertex program that you can write. And this one is actually good enough to get started. The first line here, attribute vec4 position, what that means is the word attribute means this is a value coming from the CPU. The term attribute comes from the fact that we have these attributes. Each vertex has an attribute like its position and its color. Once we get into lighting, it has like a surface normal direction. All right, these are called attributes. A little confusing in the C# world because we have our own term attribute in C#. So don't be confused when you see that in the code. But that's what that word attribute means. It's like this is something that is specified per vertex. The type is vec4. So on the shader on the GPU, tensors, vectors, matrices are first-class types. So vec4, vec3, vec2, mat4, mat3, or mat44, whatever, those are all first-class built-in types. And when you do a vector multiplication on the GPU, that's one instruction, and it's going to get executed in parallel very fast. So something very kind of deceptive is going on here. The first thing to realize is how often does this program get executed? This program gets executed one time for every vertex. So if you have a triangle, how many times is it going to get executed? 3 times, once for each vertex. If you have a square, it's going to get executed 4 times, once for each vertex. Okay, so the same exact program executed 1 time for each vertex. This program doesn't look like it does anything. It just really does, it's just a pass-through. And it just says, the position that came in, I want that to be my output position. The output position, GL underscore position, is what's used to actually render it, draw it to the screen. Okay, so OpenGL expects this to be in this default space that we talked about, -1 to 1. All right, so we're just going to live in that space today, -1 to 1. And so this one-liner, GL position equals position, is going to get executed 4 times. So there's conceptually 4 positions, and it's saying for each one, just use the same position I give you. If I wanted to transform this point, I would be doing the vector math that we talked about today, and I would be multiplying this position times a matrix. All right, but today, for this, we're just going to pass it right through. Any questions on that? All right, so this is a very simple supercomputer program. The next one we're going to talk about is the fragment program, even more simple. But the thing to know about this program is you can think about it as being run for every pixel on the screen. All right, in the general case, that's true. In the specific case, it gets run for every single pixel that is part of a triangle that's going to get mapped to part of the screen. But in the case that you're working on a game and you always have the entire screen filled, you can just imagine my fragment program. A fragment program is running for every single pixel on the screen. So if you have like a 1 megapixel screen, this program is running 1,000,000 times. That's another amazing, astounding thing about GPUs. All right, so before the vector programming, for a triangle, 3 times. This, for a low-resolution VGA screen, 1,000,000 times. And how many times a second is it going to do that? 60 times a second. If you have a decent frame rate, 60 hertz. So the most basic program is going to run 60 million times a second. So this is extremely fast, much faster than you could ever optimize. If you were drawing something, if you were drawing a plot and it started to slow down at 10,000 points or whatever the case is, you could never, ever, ever optimize that thing to be as fast as this is.
Do you mind if I ask a question?
Yes, Jason.
So these little programs, you see that they all have a name, so they are little programs. Is this actually like a little program that will get shipped to the GPU? So the GPU goes, I have the control of the pipeline, and I have each of these little programs to run in that pipeline. Is that?
That's right. So I'm going to repeat the question for the recording. So the question is, does the GPU get a copy of this program? Like we send the program over to the GPU, and then it has the program, and then the GPU runs the program based on the input. That's the question, and the answer is yes. A crazy thing is, and kind of a pitfall, is that these programs get compiled at runtime. So the OpenGL, the driver, the device driver compiles these programs and then sends the GPU machine language over to the GPU. So yeah, this is a big pitfall for OpenGL programming because you don't find out about your compile errors. Let's say I left off a semicolon. I don't find out about that missing semicolon until I run my program and until that fragment program gets compiled. Even worse, OpenGL doesn't have a concept of exceptions, right? This is a C API, all right? So if you've been back in the day, C APIs either told you about errors by return codes, or you had to check, you had to call a function, you had to proactively ask, hey, did an error happen? Well, that's the way OpenGL works. No return code help, no exceptions. You have to help, you have to ask every time you do something. Hey, I just compiled a shader, did it work? You have to ask. All right, so generally speaking, there's basically 2 steps to setting up a program in the OpenGL world. There's kind of the setup stuff that we do one time. Again, this is conceptual. For a simple example, we do this one time at the beginning. And then there's the draw step that we do every frame. All right, so the setup, most of what we do in the setup in this example is going to be compiling the shaders. All right, so again, all that compilation happens at runtime. At draw time, that's when we actually we give it instructions. Hey, remember those vertices I gave you earlier, or or here's some copy of new vertices, go draw those. All right, finally we get to see some GL code on the CPU. This is just a helper function, kind of based on something that you can get from the Xamarin startup project. By the way, as a side note, Xamarin Studio does have a helper project. You can say, hey, create new project, choose storyboard or whatever, and choose OpenGL. If this is your first time, I do recommend, yes, starting with that. It has a lot of boilerplate that you don't want to write yourself, and something like this is what's provided. In the example code I'm showing you today, I'm not doing any error checking, and I'm not doing any cleanup. In the real world, you would have to worry about both of those things, and they dramatically bloat the code, like 4 times or 5 times the amount of code because of the error checking and the cleanup. So bear in mind that I'm not doing any of that stuff today. All right, so compile and attach shader. Incoming shader type is an enum. Again, I prefer to use the word stage, but in the OpenGL world, the word is shader type. So it could be fragment shader, could be vertex shader. Again, we're just talking about what stage in the pipeline. And I'm just going to pass in the source. It's up to you where the source comes from. This can be a string literal baked into your code. It can come out of the disk. It can come from the user can type it in. It can come out of your resource, most likely. Your bundle in iOS, right? Your NS bundle, is that right? GL create shader. Again, that seems like it'd be constructing something. It is. Basically, it's just carving out a spot for you on the GPU, reserving it for you. Look at what it returns, an int. I created shader and I got an int back. What a raw deal. All right. So now whenever I want to talk about this shader, I have to pass in that integer. All right, here's some source. I pass in, I can't remember what this one is. I apologize for not putting the parameter there. It expects an array of source. Generally, you don't put anything there. The reason that that's helpful is a lot of time you'll have like some boilerplate source, like some pound defines or something that you want to inject. This doesn't help you with any like preprocessor directives. Well, there might be some help, but basically if you wanted to add like a little bit of boilerplate above your program or below it, or if you wanted to add multiple fragments of code together, you would have this array of strings. You don't have to worry about this last parameter. This is based on a C API. C APIs You usually pass in, like, if you give an array, you have to tell it how many things were in the array. So a lot of these arguments are kind of based on that strange pattern. Then you tell it to compile the shader. After this line is where you would check, did the compilation work? All right? And then you attach the shader to program. So the model here is the same as like compilation in C. You have a compile stage and you have a link stage. And so we'll see both those stages. Attaching it, this is before we link it. We're just saying, hey, we're going to link later. This is where we're saying this is going to be part of the link. So we've compiled into object code. Later we're going to link it. Linking also marries up the inputs and outputs of each stage. All right, so we're moving into what would be our setup program. All right, and so I have a member variable in my class called program. Again, this is an int. It's just an int coming back. Practically speaking, these are usually uints. So if it's like negative and maybe if it's 0, it's probably wrong. Don't quote me on the 0 thing. I think that might be up to the driver whether it starts its IDs at 0 or 1. So I usually initiate these to like -1. So I know that they're bogus. All right, I'm just putting my source inline. We already saw the vertex shader source. I'm calling the function that I had right up above right here. And my fragment shader source. And again, calling the function that I defined up above. And then again, link program. This just links all of that together, does the linking stage. Again, after this, you would have to check, did the linking fail? All right. And then finally, we get to something interesting in terms of mapping CPU world to GPU world. And you'll remember from our vertex program, we had one input basically, and we called it an attribute. That means a per vertex value, and we named it position. So the first way that we learn to map things over to the GPU is it's called getting the location. Okay? Again, it's just going to be an integer. It's not like a real address, or you can't take it for granted that it's an address. You don't know anything about it, but you just need to say, hey, give me that location. I'm going to hang on to that, and later when I need to send something to that location, I'm going to use that location handle. All right? So the one I'm going to show you today is get a trib location. A trib, again, means per vertex. It's named position, and it's in the shader I just linked called program. Got to link first. It's not going to know about all that stuff afterwards. Another gotcha I'll mention while I'm here is these are optimizing compilers in general, so they will optimize away variables and attributes and things that you aren't using. So if I had not used position here, even though I had declared that attribute there, it would have been optimized away, and when I wanted to try to get the location, it would not have resolved it. Any questions on this setup section? All right. Again, I know this, to me this feels like very ugly. It's a lot of work. This is like the most simple example that I could conceive of. Still quite a lot of boilerplate here. All right. Now we're moving into the draw phase. So the draw phase is something that conceptually is happening every frame. All right. A general performance rule is we want to do as little as we can do in the draw phase, because what happens is every so often there has to be some synchronization between the CPU and the GPU. But that synchronization is not good for performance, because the GPU, again, is this screaming fast supercomputer. And if we have to synchronize this GPU with the CPU, basically that means we have to say, hey, GPU, stop, wait. We're going to update some data. We're going to send you some stuff. And those sync points generally are bottlenecks in high-performance graphics. So we want to do as little CPU stuff here as possible. So if you are doing some big game that's doing a lot of like wild updates, like you're calculating ballistics for bullets and projectiles bouncing off each other, you might and they're not touching GPU memory. Do those on another thread. You'll have to handle your synchronization by yourself to be able to hand over whatever data needs to go to the GPU. All right, not going to worry about that much today, but you should be aware of that. First call, make current. This is a glaring example of OpenGL state and side effect. This is a base function, or it's a call to a base class function. I'll show you the context that we're in. We're in a OpenTK provided class called iPhone Game View, something like that. And it basically, but there's an equivalent call called GL make current. OpenGL, for every OpenGL call, you have to have a device context. It's also called a rendering context or a screen context or a window context. But it needs to know what's your current context. And you can have multiple OpenGL contexts. Even on a phone, it's not often done, but you could be rendering in like 4 different displays. This is commonly seen in like CAD applications where you're looking at an X perspective, Y perspective, Z perspective, and off center perspective. So you don't pass in a window handle or a window UI view to any of these functions. So when this call to make current just tells it, hey, use the current one. Clear? Yes, Jason.
So when I'm using GL and I get to this draw phase here, I guess I really have 2 questions. First one, is the draw phase being executed by the GPU as well, or is OpenGL getting results from the GPU and then drawing on the screen?
So the question is the draw phase being executed by the CPU? The code that you see on the screen right now, this is CPU code.
That is CPU.
This is being executed on the CPU.
Second question then, and this may be where the make current is there, so let's say I'm on iOS versus Android or whatever, am I getting something back from GL that I'm then drawing on the screen, or does make current basically give over the canvas to GL and GL is taking care of it and stuff on the screen?
Okay, good question. So the question is, does OpenGL draw something and then give it back to me, like some image, and then I turn around and splat that image onto the screen? The answer to that question is OpenGL takes care of it. So the paradigm is one way. So you send stuff to OpenGL and it sends it to the screen. And so traditionally, you have no idea what's happening. The very, very traditional model of OpenGL, the reason some of the API is weird is that it was like a client server. So conceptually, OpenGL can be used like you're running these commands on one machine, a client, and then these commands are being sent over the wire to a separate machine that has its own monitor or offline renderer or who knows what. And so it's just going out there into the ether, and you don't see it.
So sort of a pipeline to the screen in a sense, like that end that gets drawn on the screen. Is just set up by the fact that I'm using OpenTK for iOS, and therefore it already knows how to take care of that.
Yeah, I'm not showing. So the question was like the pipeline, how it gets to the screen and how it gets to context and that kind of stuff. I'm not showing you any of the boilerplate on like creation of the context. I can show you some of that code later. That's the type of code that I recommend that you just copy and use.
Go to new iOS project, OpenGL iOS,
Yeah.
OpenGL Android.
Yeah, go to Xamarin. Yeah, new project, OpenGL project, and they have that boilerplate there. Once you understand it, you can adjust it, you can tweak it, but it is a pain to write on your own. It's just very boring boilerplate. And generally, once you write, that's one of those examples of that thing that you write that one time, you put that away in a class somewhere, and you never write that code again. You just get yourself up above that level of abstraction. There are some tricks there. I'll try to touch on those. Okay, clear color, that just sets the background color. If no polygons get drawn, what's the background color? In this case, it's black. Again, a strange 4 component. In this case, it's RGBA, so the last component's alpha. And then I just set the color, but I didn't actually clear. Now I have to actually clear. And what do I clear? There's different buffers that you can clear. Today we're only talking about the color buffer. And so basically I'm clearing the screen. And I'm telling it to clear the color buffer, and I'm going to use black, that color that I specified on the previous line. This one is alpha, which is, especially in the case of clear color, is going to be 1. There are cases in where in like operating system composition, like you could set that to non-1, and one window would composite with another one. Generally, you won't do that in iOS. It'd probably get you not approved on the App Store. But if you want to do like some alpha blending within your app, you would have like a non-1 value there for your alpha blending. All right, remember that program that I compiled earlier and I had stored that integer? Actually, I think I stored it in underscore program. So slight typo there. This is where I use it. Basically, I say, hey, remember the program I compiled? Make that the active program. The reason we do this in the draw phase is that complicated, non-trivial examples can have more than one set of shader programs, especially video games. Video games will have a handful of shader programs that they're running. You know, one shader program for, you know, something that's shiny and metallic, another shader program for something that looks like a tree. You know, these things look very different, and so they get different shader programs.
So is this how you switch between the various programs on the GPU?
That's right.
So basically you specify which one of those individual programs are running against.
That's right. And so,
Run simultaneously, or that's not possible?
well, conceptually they're running, once they get over to the GPU, they may be running simultaneously. The way to think about this is state-based. So again, bad programming style by modern conventions. So what I'm on this line GLU's program, I'm kind of setting up my state so that the next 3 or 4 or 5 lines, I'm saying for now until you see another use program call, this program applies. So it's not really like in clock time. Yeah. But the important thing is like open. Yeah, but not current in terms of execution. Yeah, in terms of like what context am I talking about? Okay, so the next line. Oh, I forgot to do a find replace in my code. This attrib vertex. This is the value that I got back here. That should be called vertex attribute. But this is the value that came back when I called get attrib location. This is how I'm telling it, hey, I'm talking about this location right now. And I've got some data stored in vertices, which is an array, and I'm going to give that to you. And OpenGL, again, C API, very, very, very non-type safe. So basically, as far as OpenGL is concerned, you are giving it a bunch of bytes. And it will interpret those bytes any way you tell it to interpret it. So you could have an array of floats, and you could tell it to interpret it as an array of ints. All right? So it's up to you to tell it the appropriate type. There's other nuances there, like you can actually have like ints or bytes on the CPU and have them mapped to something that's float-like on the GPU. But in this basic case, I have an array of floats, and I'm telling it it's an array of floats. We'll dive into these other parameters later. This is basically what's conceptually copying the vertex data over to the GPU. We don't necessarily need to do that every draw call, but I'm doing it here. And then I'm enabling it. Seems like it should go without saying, but I'm enabling the vertices that I just sent over there. And then this is the actual command that tells it to draw. Now, a small reminder, we are not in retained mode. So again, all of these instructions are just like stacking up. OpenGL is just keeping track of all these instructions. It's not actually executing them at the time that I run them. Conceptually it is. We can think about it as like a logical flow, but this is not actually drawing anything. It's just telling it how to draw it when the time comes. OpenGL has different ways that it can draw things. So the way that I recommend you draw things when you're in debug mode is as a line loop. So that means I'm giving you a bunch of vertices, and line loop means connect the dots. And the fact that it's a loop means connect the last dot to the first dot. Which is the starting index? 0. And how many of the points are there? 3. And the very last call is called swap buffers. So a quick note about that. OpenGL draws usually what's called double buffered. And that means when OpenGL is actually drawing, it's drawing to an off-screen buffer. And then when it's finally done drawing, it swaps that buffer to the front buffer. Conceptually, well, all that happens is like a pointer changes. And so the user does not see any flicker. The user doesn't see the draw happening because it's happening in an off-screen part of memory. And then swap buffers, again, all it does is just change a pointer. And now what the video card, the block of memory the video card is pointing to, points to that block of memory that was just finished drawing. And now that back buffers become the front buffer and the front buffers become the back buffer. All right. Before I go into pitfalls and gotchas, let me show you this code in action. So I'm over in Xamarin Studio. I can definitely put this code online. This is the same code that you already saw. Here's my vertices. Again, notice that they are in this like 2D space, -1 to 1. And remember those integers I got back? I initialized those to -1. And here's the setup function you saw before and the draw function. And let's just run it just so you can finally see some graphics. There's your triangle. How low tech is that? Okay, that looks pretty ugly. I can dive into some of those. I'm not going to get into all of those parameters. I'd rather just run through the rest of the presentation and try.
Specify the color to draw those lines with. What was the white at?
Oh, good question. That's way back up in our fragment shader. So remember, we wrote the simplest fragment program that we could write. Basically said, every time that you need to draw a pixel, draw it white. Good question. So obviously you would want to pass in some, parameterize that somehow, send some information. So let me just edit this live so you can see some changes. So I'm going to change this from a line loop to a triangle set of triangles. So again, nothing has changed in terms of our data or fragment program. All I changed was the mode that it's going to draw it to be triangles instead of a line loop. Now when I draw it, you see a filled triangle. So basically we just said, hey, instead of drawing a line loop, draw in filled in triangles. A bit history there. The reason that's called begin mode is the way that we used to draw in OpenGL is we would say geo begin, triangle, geo vertex, geo vertex, geo vertex, geo color, geo vertex, geo end. And that would be a triangle. And then I would say geo begin, line loop, geo vertex, geo color, geo vertex, geo color, geo end. And it would go draw those lines. So that's why it's called begin mode. It doesn't make any sense in OpenGL ES2 or modern graphics programming. It just tells you the kind of primitive that you're drawing. So I know we're pretty way over on time. Let me show you one other quick example of like just how you can mutate this code. So I can add, the code is currently written so that it doesn't matter the dimensionality of this. Well, it gets it down here and there's a call to get length somewhere. Vertex components. Yeah. So I'm using a 2D array. I like to use 2D arrays because they force one dimension to be the same for every element, and that makes sense for geometry. So now this is going to come back as a 3-dimensional. When I run this, we'll see the same result because I just set the z-coordinate to be the same value. Conceptually, it's going to be the same. But I just wanted to illustrate. Now we're using 3 space instead of 2 space. Now let's make this a little bit, let's make it further away. So minus 0.5f. So this is going to push the triangle further back away. So what you would logically expect to happen is the triangle to get smaller. It doesn't change size. The reason for that is that by default, we're using what's called a parallel projection or an orthographic projection. The way to think about this is like it's a projection that like an architect might do or an industrial designer, where things do not get smaller as they recede into the background. So everything stays the same size no matter how far away it is. Unfortunately, we won't have time to talk about perspective projections today, but I don't want you to be thrown by that in the basic case. One thing though that we can see is if I bump this up to 1.1, now this third component has gone outside of the view. Remember I told you that box, minus 1 to 1, minus 1 to 1, minus 1 to 1. This last point is outside it. So what's going to happen is that last point is going to be clipped. But it's still going to draw the triangle up to that plane. So what we have now is a triangle that's receding upwards into the background, and at this point it encounters the z equals minus 1 plane, and it gets clipped from there beyond. So this is a way that even with a parallel projection I can prove to you that there is some depth here. And so you can play with it. So you can see how very easy it is. There's so many ways to, if I was to make these minus 2, if I made these like 10, 10, 10 or whatever, you would see nothing. Okay? Most people's first GL programs look like this. You get nothing. And what do you get on the output? You get no output. Again, just to show you, like, let me fix this. Let's put an error into my code. I'm going to take off this semicolon here and run. What's going to happen? Nothing. The program is fine. It's running fine. There's no output here on the console. Everything's fine. No exceptions. You have to check, was there an error? This is pretty bad because you can even like corrupt memory. You can create like some really, you can crash the program so you will know something went wrong. But if you look at the call stack, you won't have any clue. So it's on you to be very careful, very diligent to clean up, check errors. Down here is the boilerplate. Again, this is mostly generated. This stuff, display link, that's what Apple provides to sync you up with the display rate, to sync you up at drawing at 60 hertz. And then the other stuff is to get your rendering context. Again, what's that?
Is the GL code itself pretty similar between the three platforms, so that you could have the part actually telling you what to do in a separate assembly or something like that?
Yeah, good question. The question was how portable is the actual GL like drawing and setup code, not the device context code? And yes, that's exactly the same. That's the good news. It's like it's exactly the same. OpenGL in that context is highly portable. Like you can take, as long as you have the same version. So one area where people have griped is like somebody had an old OpenGL 1.0 program that they wrote way back in like 1993, and they complained that it wouldn't run on an iPhone. Well, actually, they were able to tweak it not too bad to get it to run on an iPhone. But assuming like you're using the same version of OpenGL everywhere, it should run virtually unmodified. The one caveat to that is that different devices have different capabilities. So like, for example, your texture size. Like if you're using images for textures, on one machine the max texture size might be like 1K by 1K. On another machine it might be 4K by 4K. There's ways to find out about that, but and again, that's going to be runtime. It's all going to compile, but you'll find out at runtime that something might not work. Okay, again, just because my worst fear is like that you guys go home and work on OpenGL code and you get frustrated because like it's not working. So that's why I really want to hedge and like just enumerate a bunch of gotchas but I'll share this presentation so you have them. But there are so many. This is very low level. Okay, the first one. This is going to seem so dumb. The reference. If you go to references in Xamarin and you look for OpenTK reference, there's 2, and the one you want is this one, -1.0. OpenTK has its own set of little pitfalls. It's open source software, so if you've dealt with open source software a lot in your life, you know what some of those pitfalls are. Like, oh, I need to go build from source because someone just checked in a bug fix that I need. That has happened to me with OpenTK. I think the good news there is like Xamarin is kind of keeping an eye on it because it's in their interest that it works well. But like if you're running OpenTK desktop, Mac, not as many people are doing that. So you might need to go build from source. Up until recently, it was unclear if OpenTK was still being maintained. It's maintained by a guy called The Fiddler, and he was on GitHub, but people weren't sure if he was the Fiddler. And this guy had forked it and started maintaining it, and oh, maybe that's the real guy. But okay, finally he forked from that guy, and now finally I think we can be sure that it's on GitHub, OpenTK/OpenTK. It looks like it's being maintained again. Big gotcha. Anyone familiar with iOS programming and Xamarin, and probably true for Android, just because something works in the simulator does not mean it works on the device. This is doubly true for OpenGL, because when you're running the OpenGL code in the simulator, it's being hardware accelerated. But guess what? It's being hardware accelerated by your device, by your MacBook Pro's GPU. Okay? So you can do things in the GPU on your simulator that would not work on the device. Graphics programmers traditionally have to have a device plugged in for their test, code test cycle. Same goes for performance. We all know this. We should know this. Simulator performance is not an indication of device performance. Doubly true for the graphics. There are lots of things that you don't get for free. One of them is like device rotation. So if I run that program that we just wrote, is it gonna, oh, it's still broken. You'll see that did I fix the code? No. You'll see that the triangle gets stretched. Because you don't get any device rotation for free. So if you want to maintain aspect ratios, you need to reset up your viewport, which we didn't talk about. We just talked about the default viewport, which is like a square. Well, guess what? In neither orientation am I a square. So realistically, unless you're a game, you need to handle this. Thread affinity. Traditionally, OpenGL is not multi-threaded. iOS just added support for this. I've never tried it, so I don't know what to tell you. But they just have a switch that you can turn on. I don't know what the implications of that are. But in general, if you're going to synchronize, you're going to send stuff to the OpenGL, you have to be on the UI thread. Error checking, we talked a lot about that. It looks like there is some saving grace here. According to the OpenTK change notes, in debug mode, he will throw an exception. I haven't tried that, but that would be wonderful. Again, I told you, reinterpret. The graphics card will reinterpret it however you tell it. So it's up to you. Shader compilations at runtime. Something we didn't talk about. There's a lot of optimizations that happen. Traditionally, when you draw things in 3D, you only see the outside of the object. So what happens? OpenGL doesn't draw the inside of the object. Well, what does that mean? How does it know inside from outside? If you draw a triangle, one triangle, there's an inside and there's an outside. There's a back face and a front face. The way that we determine that is by a convention. The convention is the winding order. What order did you specify the triangles? Did you specify them clockwise or did you specify them counterclockwise? All right. I don't remember it off the top of my head. I think the default winding order in OpenGL is counterclockwise, meaning right-hand rule, my thumb points front. So you might draw a triangle, you might have everything right, but the triangle still not be drawn because it's facing the wrong way. That's one of the reasons that I recommend starting with line loops, because they'll be drawn either way. You can also disable this feature. It's not good for performance, but it's good for debugging, and it's done with this line, GL disable, coalface. Again, totally up to you to clean up things. You do need to dispose things. In OpenTK, a lot of things implement iDisposable. I hate iDisposable. You got to do it. Vertical sync, that comes from the days of CRTs when things actually had to be synced to the vertical refresh. You want to use that for high frame rate, fluid, interactive graphics, 60 hertz. That's in Apple terminology, that's called CA display link. We talked about this, order matters in matrix multiplication. You will see, when you go there, the good news is there's lots of websites and people posting questions on Stack Overflow. Many rookies have a hard time with OpenGL. It's very normal, so you see lots of questions. One of the most common things that you see questions about is like the geometric stuff. Accumulating rotation is non-trivial math. The keyword to search for there is something called quaternions. I can talk about that next time if you want, but it's non-trivial if you want to be able to represent like a 3D object that's like flying through space. There's a bug in iOS or Xamarin. If you have your shaders and you put them in your NS bundle resource and you go make a change to that and hit run, if you made the change such that the shader is shorter than it used to be, it's like a buffer bug. The bundle will not be updated. It will have your buffer, it will have your resource and the leftover, like whatever was in there before. So like if I made my shader 10 characters shorter, the last 10 characters of my shader will be whatever was the last 10 characters last time. Your shader's not going to compile. You won't have any idea why. I think this is why in the Xamarin default project, they print out the shader code that they're about to compile. That's a good practice because of this stupid bug. There's yes. If you change your shader and your shaders are in the resource, do a clean or do a rebuild. I think that works most of the time.
It's kind of like when you use T4 scripts in Visual Studio, you forget to rebuild the T4 scripts.
Yeah, like T4 scripts or some kind of generated code or code behind. Yes. You can send values to shader that aren't necessarily wired up. Random things can happen. A goofy thing, this is another way to make your shader not compile. If I were to change this to 1.1.1.1 instead of 1.0, 1.0, 1.0, 1.0, we will get a black screen. The reason is the shader will fail to compile. You don't have a free... Oh, I stand corrected. Did I do something wrong? Okay. Maybe I'm wrong. Actually, maybe... Okay. I might be wrong. But I thought that didn't compile. They might have fixed that or become more lenient about that. In the past, you had to... 1 was an integer and 1.0 literal was a float, and you didn't get that conversion for free. Again, those sort of things, they're up to the driver. The driver, the video driver, the display driver is responsible for compilation. So one of the reasons that might have surprised me just now is like, the driver can be changed and updated. That can go the reverse direction. So you can be bit the other way. So it's really important if you have graphics code, like when a new version of iOS or new hardware comes out, to test it. Okay. There are so many references. These are just my favorites. There's a YouTube video called The History of the Teapot. If you are making a game and you're not an artist, like myself, I'm not an artist, there's a website called TurboSquid, and you can buy cheap models, assets from artists for cheap. That's a good way to get something that's not programmer art into your game. Stack Overflow, tons of stuff. Nihi tutorials, those are he's he's been doing OpenGL tutorials since the beginning. The orange book is the, I think the OpenGL ES book, or actually it's the GLSL book. It's the book on, which is the shading language. There's also the red book. And then as I mentioned earlier, just recently in iOS 7, they added multi-threading support. And in iOS 5 or 6, they added something called GLKit, which I didn't really talk about today, but it kind of helps with giving you the device context and filling in some of the other OpenGL holes. 9:10, only 2 hours and 10 minutes.
Very important.
Thank you.
Got 3 questions. Hopefully
Yes.
I can remember them all.
Okay,
So,
Sean.
the first one
3
is,
questions.
Almost in all games that I see that I download, the entire screen is a GL view.
Yes.
And anytime they need to have UI to do buttons, whatever, it's always
Custom UI.
rendered UI, not UI kit. Is there some difficulty mixing GL and UI kit? Could they use UI kit if they wanted to?
So the question was, can you mix standard UI and game or OpenGL UI? The answer is yes, you definitely can. I do that. You and I both work like in the scientific computing world. So if you're like I think you said you're in finance. So if you're in this kind of world and it's normal to have plain vanilla UI, yes, you can definitely certainly do those side by side. Can you overlay them? Yes, you can. Generally, that is a little bit dicier, like historically, but I'm going to say like I'm 90% sure that will, these days you will be fine. Like it handles it in terms of like the composition. Yes, you can do that.
Right. Second question is, I'm used to core graphics, the 2D vector graphics API that Apple provides, and so there's splines and all these things that you can do with the vertex, your vertices, curved lines, etc. Is any of that in GL? Like you did, straight lines between those points because you've done a curve through them by spline or all cubic splines, all that kind of stuff.
So the question was, is there any of the nice like vector drawing stuff like splines in OpenGL? The short answer is no. Historically there's been like a handful of approaches to that. I think there was like in the fixed function. I think there was a way to do that and have the GPU help you compute like NURBS and Bezier. The modern approach to that is to use something called the geometry shader or the tessellator. So those are new stages in the pipeline. I have to claim ignorance, like I don't know where iOS world and OpenGL ES world is with respect to those, but thank you. Those things are very advanced on like desktop and workstation. So generally what people do is if you want like higher detail, smoother surface, you will calculate those subdivisions, that smooth surface on the GPU using something like the tessellator or the geometry shader.
Third question maybe is kind of related to that one is, one day I decided I want to write a 2D vector drawing program. For example, TouchDraw is a famous Xamarin built app that's it's a very good vector-based drawing. You can draw a spline, you can actually sign your name, and then it's got all this hit detection. You can move these things around, etc. It's pretty fast performing. So I tried to recreate that using core graphics, UI, etc. And doing my own hit detection and calculate, okay, does this point intersect this spline? So I had to look for algorithms to calculate all that kind of stuff. So I got pretty far, but then the more I used it, the more shapes and objects I had on there, performance went to hell. Because it's CPU. So then later on, Apple comes out with SpriteKit. And so I watched the WWDC, I think it was last year, they did a SpriteKit demo and all this fantastic things you can do. It looked really good. So okay, so I looked in SpriteKit real fast and it said, sure enough, there's a shape node that allows you to do a vector graphics node in SpriteKit. I said, okay, great. SpriteKit supports vector nodes. So I did it all, and the performance was just as slow as what I had done before SpriteKit. So then I decided, okay, since my particular app at that time was just colored squares, I can do that with bitmap. So I switched from shape node to sprite node, which is just, you can have an arbitrary bitmap or just a colored square. And performance was 60 frames a second, fantastic. So, Sprite Kit is using the GPU to do all this drawing, but it seems like it's only fast if it's bitmap based, not vector based. What am I missing?
Well, I don't know, because I don't know under the hood what's happening. Based just on that, what you told me and kind of the context of your previous question, I would guess that they are calculating the spline on the CPU, but I don't know. It's not necessarily true. You can do it on the GPU, and so that would like force I have to calculate this on the CPU and then send it to the GPU. Other things, it's like it just depends on the way that it's composited. So like the way they're doing their composition, if it's recompositing everything, every frame, and you've drawn like 100 things, basically the question would be to test that is, does it get slower the more things that you draw?
Mine did. Yeah.
So that means that it's recompositing everything every frame. So if you have like in things, then your drawing is order in. All right. One of the reasons that graphics are so fast, GPU graphics, it's order in, yes, in terms of like however many vertices you have, but in terms of what's drawn on the screen, typically that's proportional to the screen resolution. So it runs the fragment program once for every pixel on the screen. That's not 100% true, but it approaches that. And so you get like kind of like constant time frame rate because you're not increasing your screen resolution all the time. But again, I'm just guessing. I don't know how SpriteKit works.
I eventually abandoned SpriteKit and went back to UIKit just to do my little square program, but I abandoned the 2D drawing program. I'd love to talk to the touch draw guys and see how they made it so fast.
I'm guessing, the way that I would implement a program like that is like every so often you would need to bake a bunch of layers together, and you rasterize it.
Yeah.
It's not vector anymore, it's baked.
Yep.
And then when the user clicks on one of those, you got to like unbake it. I'm guessing they just have to do stuff like that.
I guess I was hoping SpriteKit would do all that for me.
Yeah.
That if I'm moving a shape node around, it's already bitmapped it, so I'm just bitmapping it. When I let go, maybe it turns it back into
Oh, okay.
But wasn't that level.
Yeah. Well, another thing that can be happening, Apple is very particular about the way, like for example, typefaces and fonts work. For a long time, and I know I'm going down like historical road, but for a long time there was like a Microsoft way to do fonts and there was an Apple way to do fonts. And those of you who remember this might remember this kind of debate. Microsoft, when they designed fonts, they had the monitor in mind. So the fonts respected the pixels. So like they designed their fonts such that they would line up on pixel boundaries. And so, but Apple said, no, we want our fonts to be designed like the way typefaces. They don't care about pixels. They're just what your resolution of your monitor is what it is. We're going to design our typefaces based on these beautiful historical vector design for typefaces. Well, the result was back in the days of like VGA, people said Microsoft fonts look crisp, Apple fonts look fuzzy. That's because Apple fonts had to be anti-aliased everywhere because they never lined up to pixels. You would have like a letter I would look fuzzy because it would be like halfway in this pixel and halfway in this pixel. And Microsoft, it would look crisp, perfect letter I, Well, it's kind of shifted. Now you look at Apple's look crisp and Microsoft's look kind of crummy. And really, Microsoft switched. Now they use ClearType, and I think it's all anti-alias now anyway. But the point is, Apple's been anal about anti-aliasing and composition of vector shapes for a long time. They have a lot of experience with it. And so when you draw a vector shape, the reality is it does not line up on pixel boundaries. So when you have like a shape like this and a shape like this, at this point, that the way you color that pixel is actually a function of both of those shapes. It's anti-aliasing and it's blending both of them at that pixel for it to look nice. My guess is if you're using ShapeKit, they're doing that all the time. So if you have like some text or some complex shapes, as you drag them around, they're recomputing all that anti-alias results, recompositing all that stuff. So they would not be satisfied by taking a cookie cutter raster snapshot and dragging it around.
I noticed that, like, for example, when I use form text in iOS to draw custom fonts, a lot of stuff, very design heavy, so I need to realize sometimes I'm not going to choose the font and stuff like that. Then when I would do core text in iOS, it's very slow. I end up having to do tricks like rasterizing, creating a canvas and putting all your text on it in the background and then turning it into a bitmap so that you can pull it into the screen later.
Right, yes.
It's just too slow.
Yeah, you got to raster it.
But like when I go on Android, this is still anti-alias, but my guess is they're probably a little more accepting of it not being quite as perfect, that like no problem.
Yeah.
I think that there's something about that UI canvas, the non-G-core graphic kind of canvas that iOS has. It is slower than the other two platforms, hands down. You're probably right. It's probably because lead designer there is like, no, every pixel has reacts over here. I don't care if they can't see it.
Yeah.
That whole Steve Jobs, you got to paint the back of the fence thing.
Yeah. Well, thank you guys for your patience. I know you've been here for an hour and a half, 2.5 hours. Thank you guys.